In this chapter, we are talking about ideal gases and their properties related to them, and how we can use ideal gas assumptions to solve different problems. So, ideal gas only exists at certain conditions. So, ideal gas applies best at high temperatures and low pressure. All right, and some properties of gas you might already know. We have temperature, pressure, volume, specific volume, density, amount, so this is our moles, and of course, mass. So these are different ways that we can describe a gas that we might have, and you'll see how ideal gas properties apply to each specific variable. So in Boyle's law, we describe Boyle's law as, write our definition in red, so at fixed mass, or a given mass or moles, pressure is inversely proportional to volume. So this means we also have a constant temperature. And this model represents Boyle's law. So for Boyle's law, because we have a constant temperature, so constant temperature should Q to U isotherm, it relates pressure and volume, where volume is inversely proportional to the pressure. So that's why it generates this kind of curve on our graph. If we were to graph y equals 1 over x, it would look exactly like that, right? Because y equals 1 over x looks like this. Right, and that makes sense. That aligns with the shape of our isotherms. And so obviously at higher temperatures, isotherms are going to be placed higher and higher on the graph. And this is similar to our PV diagrams. And as you can see, we have these same parameters on our x and y axis, except this is just plain volume, not specific volume, but it's to be expected that the shape is roughly the same. All right, so the model that we use to describe Boyle's law is P1 volume 1 is equal to pressure 2 and volume 2. So that is Boyle's law. Now moving on to Charles' law. So for a given mass or mole, our pressure, at a constant pressure, so instead of temperature, we're fixing pressure. The volume is directly proportional to the absolute temperature in Kelvin. So that is represented by this model. And this looks more like y equals x on our graph, right? Because it's directly proportional. So since we are keeping a constant pressure, that should Q to U that we are using isobars, same pressure, isobaric, right? And because we said this process was linear because they are directly proportional to each other, our volume and our temperature, then we can expect our plot to be linear in the positive direction. So as our pressure is, I'm going to write this, as pressure increases, slope decreases. So an isobar line means that this whole line all has the same pressure as temperature and volume change proportional to each other. So that is an isobaric process for Charles' law. Oh, and we represent it with this model here. So V over T is constant. So this is V1, T1 equals V2 and T2. This represents our Charles' law. Okay, so if we combine the two, we now have three parameters. So we have P1 volume 1 over temperature 1, and this is proportional to pressure 2, volume 2, and temperature 2. So the ratios are going to remain the same for both systems. And we can use this to identify an unknown if we're given the full conditions of one gas, or one, I guess, like condition of gas, right? And we can use this equation to solve for our values that we are missing. So now we're going to talk about equation of state. So the equation of state that we are using for ideal gases, pricing this one before in high school, is PV equals nRT. I'm going to identify some things here. So this is pressure. It could be in ATM, pascals, kilopascals, you name it. This is our volume in meters cubed. This is our moles. And this can be regular moles or kilomoles. And this is our universal gas constant. So we're going to talk about that in a second. And this is our temperature in Kelvin. So it doesn't really matter which one of these we use for our R. But what does matter is that, it doesn't matter which value we use for our pressure, as long as it's consistent with the value we use for R. So R is a universal gas constant, and it relates to different variables. So most commonly used is 8.314, and our units are, and this would be equal to pascals meter cubed, or mole times Kelvin. Right, and this makes sense because if we rearranged to isolate for R and just did unit analysis, this would be PV over NT, right? And that's exactly what we've got. We've got pressure, volume over moles and temperature. 8.314 can also be modified to describe kilopascals over kilomoles, keeping our meter cubed and our Kelvin. R can also be described with ATM values. So this is a more obscure one. So the 0.08205 can be used to describe liters for our volume times ATM over moles times Kelvin. So those are some different ways we can describe R as long as it stays consistent with whatever units we're given for our system. So I can write this out. This can also equal liters. Okay, so once we do some example questions, those values will become more clear. I guess another thing I should also talk about is we can make this equation look simpler if we made it equal to, right? So this V subscript M is what happens when we get our volume over our moles. and this is called molar volume. So some questions will bring that up, and you'll see later what I mean. So partial pressure. So if we have a gas mixture in a container and we want to isolate just for specific values of one gas, then we can use partial pressures, where the partial pressures of all of our individual components adds up to the total pressure. So for this one here, the partial pressure of substance 1 takes into account only the moles of our whichever this N1 gas is, right? And then similarly for our second gas, second partial pressure, which is represented with a P, the subscript of whatever it is, and a line over top, takes into account the number of moles only for that second gas. So this comes from our PV equals nRT. And if you just isolated for P, this becomes nRT over our volume. So that makes sense, right? That stays consistent with our ideal gas law. Okay, so again, this is our full pressure is equal to P1 plus P2 plus whatever, as many gases as you'd like. Okay, so now we're going to go through an example. This is a bit of a long one, so bear with me and we will make it through. A frictionless and leak-free piston can move up and down a cylinder whose diameter and height are 10 centimeters and 1 meter, respectively. So let's label that. So diameter is 10 centimeters, and we said our height is 1 meter. At equilibrium, the downward force of the piston due to atmospheric pressure is 100 kilopascals. We also need to include the weight of our piston, and the upward force from inside the cylinder causes 150 kilopascals to push back up. All right, so it's filled with ammonia at 20 degrees Celsius, which maintains the piston to its initial location of 80 centimeters, height of 80 centimeters. So let's calculate the mass of the piston first. So let's draw this cylinder again. This is for part A. So we have two kinds of exerting forces. We have from internal forces, pushing upwards on the piston is 150 kilopascals, where a kilopascal is equal to a kilonewton per meter squared. So we have our upward force, as well as our atmospheric force that's pushing 1 kilopascals down, and the weight of our piston. We know the weight is defined by mass times our gravitational force, so we can use this to find the mass of the piston near the end of the question. So first things first, let's use our upward force and let's find upwards force in kilonewtons. So this means we're going to take our pressure and multiply it by the area of piston, right? Because that's the area that our force is acting upon. So our area, since it's a circle, is equal to pi r squared, which is equal to pi. And since our diameter is 10 centimeters, that means our radius is 5 centimeters. I'm just going to change that to meters, so 0.05 or 5 centimeters squared, and this is 0.05 squared times pi, and this is equal to 0.0078539 meters squared. So that is the area of our piston in meters squared. So then to find our force, this is equal to, so we said kilopascals is equal to kilonewtons over meters squared. And then when we multiply this by our area, meters squared, we see that our dimensions are consistent because our meters squared cancels out, leaving us with our kilonewtons of 1.17809 kilonewtons. And let's just turn this into regular newtons, which is 1,178.097 newtons. So that's the first part of our question. And the second part wants us to find the downward force. So I'm just going to continue over to this page. So our downward force so our net downward force is going to equal our atmospheric pressure plus the weight of the piston. So if we do this, this will equal so this is so 100 kilopascals, and we want to multiply it by the area of our piston once again. And this is plus our gravitational force. So this is equal to so it's 0.78539 kilonewtons plus 9.81 times our mass. And let's just turn this into regular newtons. So this is 785.39816 plus 9.81 m. Okay, so now we want our net forces. So net total. So our downward forces, let's have them as a negative component. So this is minus 785.398 minus 9.81 times our mass, and this is plus the upwards force which we found in newtons, which is 1178.079. These are all in newtons, so we're good with our consistency. So then that's this minus, oh, actually, another thing to add, we want our net total to equal 0, right? Because this is at equilibrium. So our upwards and downward forces are the same. So we want that to equal 0 newtons. So when we move this stuff over, so this gives so this is negative 392.699 equals negative 9.81 m. Let's get rid of that negative in there. All right, and isolating for m, we get, awesome, we get 40.030 kilograms. So one of the most important things from this question, keep an eye on units, know how to get kilopascals, and know to turn it into just plain newtons, or else our units for mass would have been screwed up. So that is how to do part A. Moving on to part B. Calculate the mass of NH3 in the cylinder. So what we can do PV equals nRT. And let's start by isolating for N, our moles. So N equals PV over RT. And do we have that? I believe we do. So inside, our gas exerts a pressure of 150 kilopascals in a volume of, so our volume is pi r squared times our length. It's our volume. And our height in this case is our 80 centimeters for part B. And then this is over, actually, you know what, let's solve for this right now. So then our volume is 0.05 squared. It's our radius times pi times our height, which is 0.8 meters. Then we can do 8.314 kilopascals meters cubed over kilomoles per Kelvin. And we need our temperature as well, which is 20 degrees Celsius, which we want to be in Kelvin. So we add 273.15 to turn it into Kelvin. And when we calculate this out, N is equal to, so that's 150 times 0.05 squared times pi times 0.8, that's our height, divided by 8.314, our universal gas constant, times 20 plus 273.15. And this gives us 3.8669 times 10 to the negative 4 kilomoles. Okay, so now that we have our mass, we can use our molar mass equation to find out the rest. So, where our molar mass is equal to our mass over our moles, we can rearrange to isolate for M, our mass, which is equal to our molar mass times our moles. So the molar mass of ammonia is going to be, so that's 14.01 for our N plus 3.03 for our 3 hydrogen, and this gives 17.04 in our units kilograms per kilomole. So this will give us an answer in kilograms, times our 3.8669 times 10 to the negative 4 kilomoles. And this gives us 0.00659 kilograms. And let's change that to just regular grams. So then this is 6.589 grams of our gas in the cylinder. So moving on to our last part, I'm going to skip C for now, but if you guys would like to try it on your own, our answer is 60 centimeters, right? So I'll give you just like a rundown of C. So C is like saying we have our atmospheric pressure, we have the weight, and now we're adding another downward force from our new weight. And we want to find what our new height is once the system establishes equilibrium again, right? So it just wants to ask how our height is changing. So since there's more downward force, our height's going to compress, become smaller. So it just wants to know what our height is of our piston if we add that new weight on top. Okay, but we're going to skip that one for now, and I want to look at part D for this question. So find the temperature at which ammonia in the cylinder must be heated to move the piston back to 80 centimeters. Right, so this is where our question from part C comes in. So we want to change it from 60 cm and go back to 80 cm and find the temperature at which this happens. Okay, so I lied. We're going to do a little bit of part C because we need what our pressure conditions are when we start. So we know our net force is meant to be 0, right? Because we are in equilibrium. So our downwards force is going to equal our upwards force. So we don't know what our upwards force is, right? We don't know what the gas is exerting. So that's what we are solving for. But now we have atmospheric pressure, we have the weight of the piston, and we have an additional new mass added to it. So, same as always, let's calculate it. So, this is our downward force. So this is equal to, so our 100 kilopascals for our atmospheric pressure times our area, which I believe was, where is it? Okay, 0.7853 meters squared. And this is plus our 9.81 times our mass of our piston, which we determined to be 40.030 kilograms. And this is plus 9.81 of our new mass. This is 40.03 kilograms. So then that gives us because that's this times 100 plus 9.81 times 40.030 plus 9.81 times 40.03. Okay, I think I messed up in my calculations, but this is meant to be 1.571 kilonewtons, or 1,571 newtons. So this is also equal to our upwards force. So for this question, so we want our new volume, so our volume at h equals 80 is equal to 0.05 squared pi times 0.8, and this is equal to 0.006281 meters cubed. We have our new pressure, which is equal to our kilonewtons over our area of our piston. That was 0.007853 meters cubed, and this turns into kilopascals, which is 0.571 divided by 0.007853, and this becomes 200.051 kilopascals. That's our new value. And what else do we need? And our moles we found, which was, from our previous question, 3.8669. times 10 to the negative 4 kilomoles. And now we can solve for our temperature. So this is PV equals nRT, and we arrange for temperature. This is PV over nR. So T is equal to, so our pressure times our volume over our moles and over our universal gas constant. And so now, when we do all of our math, all of our calculations, this turns out to 390.973. And remember, this is in Kelvin. So to go to degrees Celsius, we're going to subtract 273.15, and this becomes 117.82 degrees Celsius. All right, so that's how we can use ideal gas law to help us find different equations. Of course, looking at the conditions for these, this wouldn't necessarily be an ideal gas in real life because ideal gas exists at high temperatures and low pressures. And this is none of those, but this is not asking us to make any real gas law calculations, so we can assume it's safe to use ideal gas law. And like I said, you'll be using ideal gas law when you get into real gases, just to help you set up some estimates before you get to some better, more accurate calculations. So that is the first part of our video for recapping ideal gases for week 4 of Chem 201. In the next video, we will be going through some practice questions as per usual, so I will see you there.